Okay, we have talked about the double-sided spectrum of the signal S of F. So the final figure will be as follows. This will be F, and this will be the magnitude of the signal. Look, this will be the magnitude of S of F, and this will be F, 0, Fs, 2 Fs, 3 Fs, minus Fs, minus 2 Fs, and minus 3 Fs. Of course, you have to keep in your mind that the amplitude is scaled by 1 over Ts. Okay, the amplitude is scaled by 1 over Ts. This will be the function S of F. Of course, it will starts from minus infinity and ends at infinity. Of course, what we can conclude from this derivation, the function S of t in time domain again is impulses, but what? But it's spaced by Ts. Its Fourier transform will be what? Will be again a train of impulse functions, but in this time they are spaced by Fs, F capital S sampling frequency, and the amplitudes of the impulses are scaled by 1 over Ts. Okay, up to now we have found what the Fourier series representation for the sampling function S of t. Now let's go to the signal x of t. I have told you that the signal x of t is an energy signal. So the Fourier transformation for x of t, okay, this is the x of t in t time domain, okay. The Fourier transform for this function will be approximated as a triangle function for just explanation, no more, no less. But you have to keep in your mind something again. بس بريخوف الرجال. F axis, and this will be what? The magnitude of x capital of F. Okay, magnitude of x capital of F. This will be the 0 at the origin, and here we have B, and here we have minus B. So what we are going to conclude that the bandwidth for this signal, I mean x of F, will be 2B. Okay, so the bandwidth for the signal x of F will be 2B. Okay.
قد يا بوري كشكي أوي دوجي ويستسكري لو ما أبوها
جماعة دنق
كريدة
بس دنق. Okay, going back. Now, by now we have what? We have found the what? The Fourier transformation for x of F and the Fourier series for whom? For the S of F. Look, the remaining will be what? Will be the following. Now we are going to find out the y of f, which is the convolution between x of f and s of f. Look, this will be the function x of f, b and minus b, amplitude 1. This will be the f axis. And here we have the sampling function frequency. Okay, f-axis. Eh, 0, fs, 2fs, 3fs, minus fs, minus 2fs, and minus 3fs, and the magnitude for this will be 1 over ts. Okay, the magnitude of every function is scaled by 1 over ts. Okay, now what will be the next step? Now the next step, we are going to perform what? To perform the convolution between this function and the s of f. Of course, how? Again, we are going back to a principal property of the what? Of the delta function. Look, please. Delta function again, if we have a function, say f of t, convolve with delta of t minus t naught, what will be the result? Huh?
F of t naught.
Yes, f of t convolve with delta of t minus t naught. What will be the answer? This is a property of the delta function. If we have delta function is convolved with a function, what will be what will be the result? Huh? Anyone try to answer this question? Simple question. F of t.
It will be f of t naught. It will be f of t naught, I think.
F of t naught. Okay. F of t naught is a one. F of t naught. Really, this is when we are going to integrate f of t with delta of t minus t naught. The result will be f of t naught, as you have said. Okay. What will be the real answer? Another try.
F
yes.
of t minus t naught.
Huh?
Will be
minus t naught. F of t minus t naught.
Affirm. The answer will be f of t minus t naught. Okay. So if you are going to convolve f of t with delta of t, the result will be f of t. But if the delta of t is shifted at that time, the function again will be shifted by the same amount of t naught. Okay. So this is the convolution property which we are going to use to find out the y of f, or the spectrum for the sampled function. Well, let's go back to the f, and this will be what? Y of f, the spectrum for what? For the sampled signal. Yalla Jamaat. Now, first of all, we have what? We have x of f. It will convolve with whom? With delta of f. Okay, for simplicity, I'm going to simplify the job for you. Equation for this one will be what? Will be delta of f, okay? This one will be delta of f minus fs. Of course, for this one will be delta of f minus 2fs. This one will be delta of f plus fs. And this one, it will be delta of f plus 2fs. Okay, is it clear? By now, I have defined again the functions, so we don't have any problem. Now, going back. Now, first of all, x of f with convolved with whom? With delta f. So what will be the result? X of f convolve with the first impulse function, which is delta of f. What will be the result?
It will be x of f itself.
Yes, x of f itself. Okay, so we have x of f itself. Good. So we have to what? We have to put ticks for what? 0 fs to fs minus fs and minus 2fs. Okay, and minus 2fs. Is that okay? Now, what will be the convolution for the second term? I mean x of f convolve with delta of f minus fs. What will be the answer?
X of f shifted by fs.
Minus of fs.
Yeah. And for the plus delta fs, it will be at this point. Minus 2fs at this point. Plus 2fs at this point. For what? Of course, up to infinity. Well, what we can conclude? We can conclude the following. Look, please. That the signal y of f is what? Is the replicas of the original signal x of f. Now, the centers of the replicas are what? 0, fs, 2fs, 3fs, 4fs, and so on. Okay? And to the left side will be minus fs, minus 2fs, minus 3fs, and so on. Now, based on this idea, okay, we have 3 cases for sampling. Now I'm going to talk about it. Sorry. The 3 cases of the sampling are first case, okay, case number one, when fs is greater than 2b, okay. First case when fs is greater than 2b. Please look at this point. It's a very important point. Well, we said that this will be the y of f, okay, y of f, and this one is f. Well, now this will be fs, 2fs, minus fs, and minus 2fs. Of course, this one will be 0. Now, we said that the first replica will appears at 0. Okay, the first replica will appears at 0. Now look at condition number 1. In condition number 1, we said that fs must be greater than 2b. بس بنخبط رجاء. Look, so this will be the second replica. بس بنخبط رجاء. Now this one is b and this one is minus b. Okay, now look, if fs, this is fs of course, is greater than 2b, at that time the replicas of the spectrum will be aparted. Look, so we have here a guard band. Okay, a guard band. Here we have a guard band. Well, of course, for the others will be the same thing. Okay. Well, they are aparted. Well, so we have what? We have guard band between what? Between the replicas. Guard band between the replicas. So, sorry. Guard band between the replicas. Now, what is the benefit of getting guard band between the replicas? To recover the original signal, what we are going to do, just using a low pass filter with cutoff frequency equals to what? Cutoff frequency equals to fs over 2. Okay, with cutoff frequency equals fs over 2 and minus fs over 2. Well, so in this way we can recover the original signal without any problem. Okay, this is the first case. First case when what? When fs is greater than 2b. Second case, we have when the case number two, when fs is equal to 2b exactly. Of course, when fs equals to 2b, this is called Nyquist rate. Okay, Nyquist. This is called Nyquist rate. Well, this will be the Nyquist rate. Now, again, I'm going to redraw the spectrum for y of f when what? When fs equals to exactly 2b. Again, this will be the f-axis. Let us put ticks for fs. This will be fs, 2 fs, minus fs, and minus 2 fs. Okay, and this will be what? Y of f, or the sampled signal, or is equal to what? X s of f. Okay, either say it's y of f or say it's spectrum of the sampled signal, I mean xs of f. Now please look at this case. In this case, exactly we have the following form. Now, when fs is equal to 2b, there is no guard band. Okay, no guard band. Sorry. No guard band between replicas of the spectrum. So if we are going to recover the original signal, we need what? We need a low pass filter, but what? With sharp edge. So in this case, you need a low pass filter with what? With sharp edges. Okay, this is the problem. Well, now we have discussed the second case. The second case is what? Second case when fs, or the sampling frequency, equals to 2b. Really, this case is called what? Is called Nyquist rate. Okay, here we have, in this case, we have a case called Nyquist rate. Well, now let's go to the what? To the third case. In the third case, we have the following. Case number 3. Okay, in case number 3, fs is less than 2b. When fs is less than 2b, overlapping will occur in the spectrum. Look at the y of f, or the spectrum for the sampled signal xs of f. Xs of f, and this one is f. Again, here we have fs, 2fs, 3fs, minus fs, minus 2fs, and minus 3fs. Okay, this will be the 0. Again, I'm going to draw the spectrum. Look, now this is the third case. When what? When the fs is less than 2b. Now easily you can note that we have what? We have overlapping. Okay, we have overlapping between the frequency or the replicas of the spectrum of the signal x of t. Now, if you are going to recover the original signal, again here we are going to use a low pass filter. Unfortunately, this time low pass filter will recover the original signal plus what? Plus some sidebands from the nearby replicas. So in this case, I mean the third case, original signal or the signal cannot be recovered. Okay, and this case is called what? Is called aliasing or spectrum overlapping. By now we have discussed three cases. Okay, three cases. Case number one, when fs is greater than 2b. Of course, in this case we don't have any problems. Directly, merely we need a low pass filter to recover the original signal. In the second case, we have talked about sampling frequency equals to 2b. Of course, in this case is called Nyquist rate, and again we need a very sharp edge low pass filter to recover the original signal. And in the third case, we have discussed when fs is less than 2b, and we have said that will leads to what? Will leads to overlapping in the spectrum, and in such a case the original signal cannot be recovered. Up to this point, do we have any question? Is it clear for you, these three cases?
Yes, دكتور.
بله دكتور، بس دكتور بسيارك الفيري
بله كرم
يعني انه كاختي بو حالتا نايكوس ريت والحالتا كده ما هردو قدم ما لو باس فلتر استعمال كر بوتي شاربيج يعني ما نحن لو باس فلتر اوتوماتيكي شاربيجا
بس دوباره كجارك هذه بخير اخو واضحه.
بوتي ما شارب ايج استعمال كر حتى ما درخ استيو نايكوس ريت لو باس فلتر ما بوتي بي شارب ايج
ها بله خب ده وقتی مثلا هي سيجنالك هي continuous time signal درسته continuous time signal تحويل كي بو ديجيتال نا بيشتهنجي لازم تو يديك دي تو اي كونفرتر يعني جارك هذه بقرا بو انالوج درسته. So how we are going to recover the original signal? Of course using a low pass filter. بس بري خوب ده لو كدي ابد بسارك قالك جانا لو كدي وتا ديار كان درست دست خوش ابد بسارك قالك لاوا. Please look at this diagram now. Say we are talking about the first case. In the first case we said that the spectrum of the original signal or the replicas are aparted away and we have a guard band. Okay, now of course it's at 0 fs and 2 fs. This one is at minus fs and minus 2 fs. Now the question is how we are going to recover the signal using a low pass filter. Of course, when you talk about the low pass filter, this is an axis of f, and this will be the low pass filter response. Okay, this will be what? fs over 2, and this one will be fs over 2 in minus, of course. Now look, we are going what? We are going to pick up this one only. How? The whole spectrum, I mean, look at the upper axis and the lower axis will be multiplied together. Okay, so at this region, I mean here, this region, the original signal multiplied by 1. Outside the low pass filter, other signals will be multiplied by what? By 0. So in this way, we are going to what? We are going to extract the original signal, which is what? Which is x of f. So low pass filter is used for what? Is used to extract the original signal from the what? From the replicas of the spectrum. Of course, we said that in the second case, again, we have the ability to extract the signal or reback the original signal. In the third case, as you have seen, there is no ability to reconstruct or reback the original signal. Now I'm going to go back to the slides. Stop share, yes, to the PowerPoint slides and to continue the lecture. Well, we have explained the derivation for the sampling, and by now we have talked about the two mechanisms of the sampling. I mean, the mechanism of the in time domain, what's going on in the time domain, and what's going on the frequency domain. Of course, we have to define two important definitions here. Sampling is the process of taking a continuous time signal and representing it by a series of discrete samples. It is realized by what? Multiplying the analog signal or the input signal x of t by what? By the sampling function s of t. Reconstruction is the process of what? Passing the sample signal through what? Through a low pass filter. Look, is the process of taking these discrete samples and recreating what? And recreating the associated continuous time signal. Time domain, we have discussed this in detail. Again, the frequency domain, again, I have discussed and derived the necessary equations. All we need here, look at this. This is the reconstruction process, and I have explained it well. Now, the remaining is the following. Now, what will happen in the time domain when we are going to reconstruct the signal? Let's go back to this diagram. Please look at this diagram here. Now, as I have told you before, when we talk about the multiplication, we said that multiplication in time will lead to what? Will lead to convolution in frequency. Now, look at this. Y of f or xs of f is what? Is the sampled signal in the frequency domain. Here we have what? Replicas of the original signal. Well, now it will be multiplied by the low pass filter to get what? To get this signal, to pick up this one. Well, to get x of f. Now, I'm going to what? I'm going to represent this operation in time domain. Of course, how? Look, again, we have the same thing. We said that previously, multiplication in a frequency, taking its inverse will be what? Will be convolution in time. Now, my question is, if you have a rect function in a frequency, its inverse will be what? Will be sinc function in time. Okay? Due to what? Due to the duality, as I think you have studied the duality in the Fourier transformation. No? Okay? Duality in the Fourier transformation. So the Fourier transformation for the rect will be what? Will be sinc. And the inverse for the rect of f will be what? Sinc function in time domain sinc t. Well, this will be, we are going to use this duality to illustrate what's going on in the time domain. Well, now continuous. Now, time domain, to see how the reconstruction process works in the time domain, recall that a low pass filter in the frequency domain is what? Is a sinc function in time domain. So multiplying by a box, okay, filter in frequency is like convolving with a sinc in time domain. Since y of t is a just of a series, a series of impulses, samples of x of t, it follows that reconstructed x of t is merely the superposition of scaled and shifted sincs. Look, here we have sinc, this one again a sinc, this one again a sinc, and so on. Okay, so we have what? We have stream of sincs. How they are generated? We said that because the sinc function will be the inverse for whom? For the rect function in the frequency, and it will be convolved with the original signal x of t. To get this signal after performing the superposition, we can reconstruct what the original samples. Now it's good. By now, we have some important notes you have to keep in your mind, really. Some important points you have to keep in your mind and don't forget it. The Nyquist sampling theorem, okay? Now, after talking about sampling and reconstruction process, by now we have the ability to give some hints and some rules how we are going to select the suitable values for the sampling in order to have distortion-free reconstruction. Of course, when we are going to sample a signal, this is not the whole job. The whole job is what? Sampling and reconstruction, okay? They are connected together. These two operations are connected together. So we have to have successful sampling and what? And successful reconstruction. So in order to have a distortion-free reconstruction of a continuous time signal, two things have to happen. First one, the continuous time signal must be band limited. What do you mean by band limited? It means that the signal must have a specific bandwidth. Well, exactly like this one. Look, I mean, for example, a signal in frequency domain must have a bandwidth, okay? A specific bandwidth, not infinity bandwidth, okay? So this will be the first condition. Well, we have to obey the first condition, which is the time domain, continuous time signal to be sampled must be what? Must be band limited. Second condition, the samples must be close enough together in time. What do you mean by this one? This means that the sampling instance, okay, must be what? Must be small. Of course, when we are talking about a small time instance, okay, minimizing the time between the samples taken means what? Means increasing the sampling rate, okay, means increasing the sampling rate, which is very acceptable. From examining the spectrum for Y of F in the slide number 11, to prevent overlap, okay, I have discussed three cases. Well, we said that when Fs greater than 2b, Fs equal to 2b, and Fs less than 2b, I mean to avoid the case by which Fs is less than 2b, we have to have 1 over t minus w greater than w, or 1 over t greater than 2b, since t is known as the sampling period instance, or 1 over t is called the sampling rate in hertz. All of these implies that the grand result, that in order to achieve flawless theoretical reconstruction, well, now we have two important notes in green. The sampling rate must be greater than twice the maximum frequency in the input signal. The critical sampling rate, 2W, is known as what? The Nyquist rate. The above statement is known as Nyquist sampling theorem and is definitely one of the most powerful concepts ever seen by an engineering student. Okay. Now we have another topic. Of course, this topic, I'm going to talk about this topic in the next week, inshallah. But here I'm going to talk about the introduction for the what? For the aliasing. Aliasing again requires some derivation, not available in the PowerPoint slides. I'm going to derive these required relations in the next week, inshallah. But by now, I'm going to talk about some important points about aliasing. First of all, we said that we have three cases in the sampling. The third case, which has problems, okay, occurs problems. Why? We said that if the sampling rate or the Nyquist rate is less than 2b, at that time, what will happen? At that time, overlapping will occur, or in other words, we say we have aliasing. Okay, we have aliasing. As you know, in the case of overlapping or aliasing, the original signal cannot be reconstructed. By what? By using a low-pass filter. So first of all, let us know what do we mean by aliasing and why we don't have the ability to reback the original signal. Now, by now, every one of you and me again, we have a unique name. Nah? Okay? Everyone has his own name. Nah? Are you with me or not? Hmm? Are you with me?
Yes, you are.
Yes, teacher. Yes.
Yeah,
You-
it's okay. So every one of you has his own name, nah?
بله يا سيدة.
Tu n'avete chia, tu n'avete chia.
كي؟
Tu,
الزانم يا سيدة.
Zana, good. Now, Zana, is it possible a person have, for example, 5 names?
No, just we had the maximum 2 names.
2. So
سيدة
I'm
عندك
going to
عندك
call
هي.
you, I will call you with which one? يعني تدونا بهاي شوادي قاعد
Yeah,
تتكلم
which one you prefer you call him.
Okay. I'm saying formally, informal. Okay. Everyone
one name.
has a unique name. No, or is it okay? Only one name. Okay. So if you have more than one name, okay, how we are going to call you? For example, Zana, or say you have another name, say Hassan. Okay, I will call you Hassan or Zana. Which one? This is a confusion. No. Okay, make a confusion. Now in aliasing, we have samples. Okay, we have samples, a set of samples, and these set of samples belongs to what? To M signals. Of course, M may be 100. Oh, so these samples belongs to signal number 1, to signal number 2, to signal number 3, to signal number 4. To which signal really? We have really a confusion at that time. So to overcome this problem, we have to what? We have to put at the input of the DSP system a low pass filter for what? For band limiting the input signal and to avoid what? And to avoid this confusion or aliasing in the output signal. Of course, this title, I mean the aliasing, will be the address for the next week, inshallah. By now, I have finished the 2 lectures for today. If you have any questions, please, still we have 1 minute. We can utilize this 1 minute by your questions. If you have any questions, you can ask your questions, please. No questions.
سيدة
بله
بس في ريكورد دي كان جينا خالد موضوع ده
چه؟ محاضرات
الريكورد بله
افرودي ابلود كم نوكا بيش نفس ساعة دو ابلود كم ان شاء الله.
تمام سيدة قالك ممنون
از ممنونم سرچاوا بخيراتن ان شاء الله حفتي يابيت ام دي باخذ من لسر الليزنج ودوسي اكزامبلز دي بتحلكم لسر سامبلينج ان شاء الله في اخذه.
تمام سيدة
سرچاوا. Any questions? No more questions?
No.
Okay. See you next
Thank you.
week, inshallah. See you next week, inshallah. And goodbye.